Welcome to our statics video in which we are going to start talking about friction. This is chapter 6 in the textbook. And friction is something that we discussed in physics class. And so hopefully this should mostly just be a review. So let's start off by talking about what friction is. When two objects or substances are in motion or are trying to become in motion, and they pass across each other's surfaces or each other's molecules, there is some contact that occurs between those surfaces or between those molecules, and that contact has a tendency to want to impede motion, and there is a resulting force that we call friction. So we can describe friction in many different ways. There is, first of all, dry friction. And that's the type of friction we talked about in physics class. We talked about static friction. So if an object is at rest, like the classic example is a box sitting on the floor, and we want to push on the side of that box and get it to start moving, we're going to have to overcome the static friction force between the bottom surface of the box and the top surface of whatever it is sitting on. Then, once the object is in motion, there remains a dynamic friction or kinetic friction force between those two objects. The kinetic or dynamic friction force is less than the static friction force, so it's easier to keep an object in motion. So imagine again that box on the floor that we are pushing. Once we get it going, it will be a little bit easier to keep it going than it was to initially start that motion. Another type of friction that we talked about in physics class was viscosity. And so this is an example of fluid friction. As a fluid flows, which is what fluids do, it may be relatively easy or comparatively difficult for those molecules to flow across each other. And so this is described in terms of viscosity. So a viscous fluid resists flow. It's thick and could be thought of as, goopy, I guess you could say. It doesn't want to flow easily, whereas a very fluid with low viscosity will flow quite easily. Like water is pretty low viscosity. And then finally, we have rolling friction. This is of note to engineers because we frequently have wheels or gears or pulleys or other rotating components of a machine. And as that wheel or cylinder rolls, there is a friction force between that rolling wheel and the surface that it's on. And so oftentimes engineers want to maximize efficiency or minimize the rolling friction between surfaces. For instance, that could improve fuel efficiency in a car if you had tires with a low rolling friction. But all of that is a bit beside the point because this is, after all, statics class, and we are interested primarily, pretty much exclusively, in static friction. So static friction is a force that always goes in the direction opposite of the motion. But of course, if we're talking about statics, the objects are not in motion. The objects are at rest. However, if we apply a force to an object, we might potentially cause motion to occur. So we're going to pretty much be focused on static objects that are just on the verge of starting to move. There is impending motion that is about to occur. It hasn't occurred yet, but it is just about to. So if we look at the example down here, the little diagram, we have this force P acting to the right, and we are going to assume that that force is going to be applied. And as that force increases, eventually it will get to the point where this block is just about to start moving. If we apply just a fraction of a pound more to this box, it would start to slide. Now, the only thing preventing it from doing so, the only thing keeping this box still, keeping it static, is the friction force, F. Now, the friction force can be calculated, as you see up here, by the normal force, that's what the N stands for, the normal force, times the coefficient of static friction. So what is the normal force? Well, the normal force is the force that is perpendicular. This force makes a right angle with the surface, pushing back against the object. Now, in this scenario, where the box is sitting on a horizontal surface, the only force pushing the box down is its weight, which is caused by gravity. So gravity causes weight to go straight down. The surface pushes back with an equal and opposite force, which we call the normal force. Those two forces cancel each other out in the vertical direction, static equilibrium. But then we take that normal force and we multiply it by the coefficient of friction. Now, the coefficient of friction basically depends on the materials used for these two objects. So some surfaces are going to have a high coefficient of friction. Typically, it corresponds to the roughness of that surface. So if this surface is sandpaper or asphalt or something like that, we're going to have a high coefficient of friction. If it is smooth steel or marble or ice, that's going to be a very low coefficient of friction. But we take the normal force, we multiply the coefficient of friction, and that tells us the maximum amount of static friction that can be provided here. So if we apply a force P right up until the point where these two things are equal, F equals P, then motion will be just about to occur. And then if we apply just a small little amount of additional force, then this will go from being in static equilibrium to being dynamic or kinetic. It will actually start to move, and it will no longer be in a state of equilibrium. Now, the thing to keep in mind here is that in our first example, where the weight is acting straight down, the normal force pushes straight back up. That's fairly easy to calculate. But when we introduce forces like here in this example, where we are pushing down at an angle of 30 degrees, what you have to keep in mind is we have the weight going down. We also have the vertical component of that force pushing down and the horizontal component of it pushing to the side. So this additional downward force is going to cause additional force in the downward direction, which is going to increase the normal force. The normal force is going to have to be larger to compensate for that downward force. The other type of situation that we'll look at is when the box is no longer on a horizontal surface, but on an inclined plane. If the box is on a ramp, its weight goes straight down. And so if we take this whole ramp and rotate it so that the inclined surface is actually horizontal, that weight now will appear to be at an angle. And again, we'll have a vertical and horizontal component. Okay, so there are a few additional things we have to look out for other than this very basic type of example here. But the whole inclined surface thing, I'm getting ahead of myself a little bit. Let's focus on this problem here. We want to calculate the force P required to cause motion. So how much can this friction force resist at the point where those two things are exactly equal? So that if we apply just the tiniest amount more, it will actually cause motion to occur. First, we'll look at this situation where the the only force in the vertical direction is the weight. and we're going to pull with a force P that is perfectly horizontal. The coefficient of friction is 0.4. Then we'll look at a situation where the force P that we're applying is not horizontal. Let's start off though in the horizontal direction. So the weight is 400 pounds. So if we're dealing in English units and we're given a weight in pounds, then we don't do anything to it. We just use that weight. If we were doing a metric problem where we were given kilograms, kilograms is a unit of mass. It's not a unit of force. And so in the metric system, the unit of force is the Newton. The Newton is a unit of force. And we want to deal with forces. So if we take the mass, which is in kilograms, and we multiply it by g, which is in meters per second squared, g is the acceleration due to gravity, then we get newtons. So if we were presented with a problem that's in metric, we would need to multiply by gravity. But if we're given a force in pounds, we just leave it in pounds. So the vertical force present here, which is the weight, is 400. That's the only force in the vertical direction, which means the normal force that's going to push back against that is also going to be equal to 400. If the normal force is 400, then the friction force equals the normal force times the coefficient of static friction. So that's going to be equal to 400 pounds times 0.4, which is 160 pounds. So the friction force is 160, which means we can apply a force P up to 160 pounds, and this will remain in static equilibrium. If we were to apply, say, 160.1 pounds, then that would be greater than the friction force of 160, and this would no longer be in static equilibrium. The box would start to move to the right. Okay, so what we are interested in finding in our statics class is this force that will maintain static equilibrium right up to that point. The tipping point here is 160 pounds. Okay, I think that's where I'm going to stop this video right here. We'll look at the part B of this example problem at the start of the next video.